Thank you very much, Dr. Tremblay, for sharing your valuable insights. We now continue with Dr. Leon Alkalai, founder and CEO Mandala Space Venture, and former technical fellow at NASA's Jet Propulsion Laboratory. Dr. Alkalai has played a leading role in major space missions, is now advancing the energy and space economy with a special focus on HPC and AI application beyond Earth.
Good morning. Thank you very much for inviting me here. My name is Leon Alkalai. I'm a proud PhD student of Professor Tomás Lang. I have deep and very fond memories and time spent with Professor Lang. As mentioned a little bit earlier, we became wonderful friends with a family and amongst ourselves, and he was a great mentor. He was pretty tough as a professor, which we as PhD students, we appreciated. And we'll talk more about Tomás Lang this afternoon. But a few things I wanted to just share with you is that when I got my PhD at UCLA in computer architecture, I looked around, as all of us did at the time, for where I'll start working. And I had a number of different offers, HP Labs, Bell Labs, Bell Core, even from a company in Japan. And then I also had at the time, a fellow from JPL that some of you may remember the name, Kim Gostelow, came to recruit at UCLA, and I just signed up to interview. And it turned out that if you remember from there was a theoretical machine, Arvind Gostelow from MIT, that did functional programming and so on. It turns out that the work that I had done at UCLA as my research, I read all the papers of Kim Gostelow, who came to recruit. So we ended up really having a wonderful conversation, and JPL, NASA's Jet Propulsion Laboratory, decided to invite me for an interview. And then I basically said, I will accept an offer from JPL if they match my highest offer from industry, which they ended up doing. And I ended up at NASA's Jet Propulsion Laboratory. Those of you who don't know, JPL is in Pasadena, in the Pasadena area. It is a pretty large institution, meaning that it's been responsible for most of the NASA robotic space explorations. Not all, but most of them. Certainly all of the larger missions that you might recall from history, the Voyagers and Galileo and Cassini and so on, all the Mars missions are generally from JPL. So I'll tell you a little bit about myself and my career. And I'll tie it actually to Mark and to Matteo and others that are talking today, because in a kind of strange way, I'm making, in my career, a full circle from computer architecture, computer science department into JPL, doing missions to the moon and Mars, and then coming back to high-performance computing and AI in space, now in a capacity of a private career when I retired from JPL 4 years ago. So I'll tell you a little bit. I got my PhD with Tomás Lang and Professor Milo Herzegovec, went to JPL, and the job interview I had at JPL, and the first project was actually called Remote Exploration and Experimentation. It's not shown here. The acronym was pretty poorly chosen, REE. It didn't mean much. But that was the job description that I applied to. And I was a science fiction kind of a geek. I loved Isaac Asimov and many other science fiction writers. And I had imagined the HAL computer from Odyssey 2001, this AI computer system with optical computing, optical data storage, lip reading, emotional, and so on. And I imagine myself working on AI in space for deep space exploration. I was kind of confronted with a rude awakening that my first project was the Sojourner rover on Mars that had the 8085 Intel controller inside the rover, the little mini rover, which was really going back in history, not forward. But what I learned from JPL at that time is that at least NASA and JPL at the time was very practical. It had to work. On Mars, move from one place to another. High-performance computing really wasn't a motivation in itself, but it became more and more. If you fast forward to today, the one metric ton nuclear-powered rovers on Mars, of which there are 2, they have lots of AI built into the rovers today on Mars. They are each about $2.5 billion in cost, the Curiosity or the Perseverance rovers. And they have onboard scheduling, they have planning, navigation, all of it done on board in terms of onboard intelligence and AI that we use today. I spent 32 years at JPL. It's a long career. I retired as a fellow, technical fellow of JPL. I left 4.5 years ago and decided to create my own little venture studio in which I incubate, I accelerate, and I invest in startup companies exclusively in the business of space. And what I hope to convince you today, maybe many of you are not necessarily aware, but there's a huge industrial revolution going on today in space. It is beyond imagination. If you haven't been following what's going on, and it's not only SpaceX, there's a huge industry today emerging to put infrastructure in space, manufacturing in space, lots of stuff, and yes, data centers in space, which you'll hear from me as well. So I created Mandala Space Ventures. Those who don't know, please look up what a mandala is. It's a Hindu-Buddhist symbol, and it has relevance and connotation in space. And I found that to be meaningful, and we called my company Mandala Space Ventures. The venture funds that I've created, Explorer 1 and Mariner 2, are investment vehicles to invest in space companies. I'm very proud to have the pioneers or the real mentors and leaders in the space program on my company advisory board. This was the kind of founding of Mandala Space Ventures. To my left is Dan Golden, who used to be the head of NASA for a decade. To his left is Charles Zelachi, who was the director of JPL for 15 years. And Congressman Dave Dreyer is to my right, and businessman Brad Schwartz. This is kind of the founding of the vision for Mandala Space Ventures. And part of that vision, which may relate to this university or certainly relates to the universities that are like Caltech, UCLA, and so on, I found that when NASA spends, let's say, $2.5 billion on a single rover, these are taxpayers' monies, that the amount of commercialization from that investment is very poor. The utilization of IP in the United States from national laboratories and universities into the private sector, I consider to be very, very poor use of government or taxpayers' money. So I wanted to leave JPL, create an entity where IP can be commercialized, companies can be created, licensing IP, and so on. So I created Mandala Space Ventures. My advisory board, as I mentioned, Dan Golden, Charles Zelachi, also a very wonderful lady, Dana Shell Smith. She was the US ambassador to Qatar under Obama administration. and Peter Lowy is a very large single family office. They used to own the Westfield shopping malls around the world, and they've invested in my company. So I'm going to give you a little bit of a kind of a general introduction to space and general introduction to what is happening today in space. And it is huge, and it's not only SpaceX. Thousands of companies are launching businesses and services in space. The market size has been growing beyond anticipation every year. There are a number of studies every year that come out predicting the scale of the economy in space. And it's pretty interesting we mainly see and learn about SpaceX and the launch vehicles. The launch vehicle business is barely 2 or 3% of the space industry. That's why Elon Musk diversified from just launch vehicles to many other areas, Starlink, Starshield, and many, many other areas, 9 verticals in SpaceX. The launch vehicle business is quite a small total business for space. I want to spend a few minutes on this slide simply to give you the big picture again of why space is important. And I'll maybe lead to the punchline in a few minutes. I really believe eventually data centers will be in space. Not Wisconsin, space. And there are many, many good reasons for that besides power, energy, cooling, and so on. It's not going to happen anytime soon. But if you believe in fusion, this is to me easier than believing in fusion, which I welcome, and I think it will happen for sure. But space is emerging as a major, major industry for humanity. No doubt about it in my mind. It may take a few decades, it may take time for it to happen, but there are so many advantages that space provides that eventually it will become part of humanity, just like we have economy on Earth. That's why I made the deal with Mark. You take care of planet Earth, I'll take care of space. And space begins at 100 kilometers, the Kármán line. Everything above is lower Earth orbit, which is about 200 kilometers up to a few thousand kilometers, then medium and geostationary and so on. So space is huge, humongous, humongous. So much room and so on. But these are the key areas that really are impactful and meaningful when we talk about space. Climate change, monitoring and mitigation, observing planet Earth daily in optical and every possible spectral band. The whole purpose of providing what we call LEO freedom of operations. There are a few topics that are problematic in space, and that is there's a lot of junk, and we need to manage that. But that is all doable. We do that on Earth with airplanes, with cars, with UAVs, and so on. So managing, even though there are concerns, there are certain effects that can be multiplicative with junk, but it's manageable, and space is just humongous. The lunar economy, I'm not sure if you've been following, but there's every year more and more missions going to the moon. Landers and building habitats and so on. It is going to happen. And then there are many companies going into managing and bringing resources from beyond Earth, including helium-3 from the moon, which is needed for nuclear fusion and so on. But what's happening, what is enabling, what are the key drivers? The reduction in the cost of access to space is just phenomenal. Every year, the cost of getting to space goes down, and the up mass, the amount of mass going into space, is growing exponentially. The Starship, which now is proven to be successful, at least recently, can launch into space 100 metric tons in lower Earth orbit. That is just a breakthrough technology. You can launch buildings, huge facilities in space with a single launch. And there are many besides SpaceX. Blue Origin, Rocket Lab, Firefly, Relativity, many companies that are doing the same. Global communications, you have Starlink, you have OneWeb, you have Kuiper and Kepler, and just dozens of companies going into broadband communication in lower Earth orbit. Space is a national security priority. In the US, most of the money in space comes from national defense, from the Department of Defense. The NASA budget for space is about a quarter, maybe a quarter of the total investment in space. And that has its implications. I'll talk about that later. And then the merger of AI and robotics. That is a powerful combination for Earth and for space, which certainly is happening fast. I'm not going to go through all of these, but I want to tell you some of these major trends that are happening in space. Certainly there is a defense pivot. Not everybody is pleased about that because of how they feel about defense applications. But just going by the amount of money that the US is spending, and just again by comparison, the amount of money that the US spends in space is more than the whole world put together. So the US budget in space, even NASA's budget is bigger, civil space is bigger than all the other civil space programs put together. So the US is a leader in this field, and there is more and more money going from defense budgets into space for Earth observations, for national security, tracking fast-moving objects, and so on. So that is, if you look at topics, optical communication, space domain awareness, AI in space, cybersecurity are all key topics that are happening right now. Startup companies and lots of money going into these areas. I personally believe in infrastructure in space. There are companies that are unicorns today that are building manufacturing capabilities in space. One of the leaders in this field or applications is pharmaceuticals. The pharmaceutical companies are investing lots of money in manufacturing drugs in space. There are also companies that are investing in semiconductor manufacturing in space, growing crystals in space that will enable, when you bring those wafers back, better performance on Earth. There are startup companies from Stanford and others all doing manufacturing in space. I personally believe, and I have invested in data centers in space, you'll hear that in a few minutes. In the area of the LEO economy, lower Earth orbit, lots of stuff going on. I'm personally very excited about the one at the bottom called VLEO, very low Earth orbit. Normally, if you look at the space station, you look at Starlink, you look at all the other satellites in space, what they try and do is to go as high as possible in altitude, but still be in lower Earth orbit. The reason is to avoid the atmosphere of the Earth, which creates a drag and creates impact on materials. So there's a region between, let's say, 200 to 500 kilometers above Earth that has been a zone that everybody would avoid. Now there's technologies emerging that allow spacecraft to fly very, very low, 300, 200 kilometers, deal with a drag and accelerate, so air-breathing propulsion systems. But at VLEO, that you have, for the same power, you have better broadband communications, higher resolution imaging, and so on. So this field of VLEO is emerging very, very rapidly right now. I believe also that the lunar economy is going to grow, maybe not within the next couple of years as large as it will maybe in a decade, but there will be habitats, there will be people living full-time on the moon, mining, exploration, research parks, and so on. These are some of the topics that I like to talk about because in space, I believe a lot of the outcomes are actually predictable. We can talk about things that I believe are really going to happen where we are today. I'll just pick a few of these to articulate. the International Space Station, or at least the US role in the International Space Station, has already been advertised to basically pull back from the, to basically retire the International Space Station. And NASA's been putting every year billions of dollars into maintaining NASA's presence on the International Space Station. Well, NASA is commercializing that. There is a program called Commercial LEO Destination, CLD, where NASA has already funded companies, half a dozen companies, to build private space stations. So that is going on right now. There's a company called VAST, a company called Axiom, there's Blue Origin's Orbital Reef, there's Starlab. There are hundreds of millions of dollars going into building private space stations today. The first module is being launched in 2026 from VAST, and in 2027 from Starlab. This is happening within the next couple of years. There are consequences or outcomes that one can predict. There'll be real estate available in space. There'll be tourism, training, education, manufacturing. All of the things we know happen on Earth when somebody builds a new building in downtown Santiago. There's going to be lots of stuff going on to sell or to lease and develop a space, in this case, a space economy that will definitely emerge. Number two, heavy launch vehicles such as SpaceX, Starship, Blue Origin's, New Glenn come online, and this year, next year, and so on. The up mass capability is humongous. All of a sudden, Starship is going to want to fill that capacity of 100 metric ton per launch. That's going to bring the cost down. There'll be companies, brokers, mediators trying to get satellites from all over the world to book a capacity on one Starship launch. And that's just going to stimulate a whole marketplace of getting into space quickly and so on. So these are all things we can predict. Also, broadband communications, AI, and edge computing will become available in space. So this is the marketplace that in my new business we're keeping track of very, very carefully. I like to advertise a little bit the region where we operate in Southern California, which is really the epicenter of the, I don't know if that, I use that in California, but it applies to Chile too, the epicenter. But the concentration of companies in Southern California is kind of like the AI in Silicon Valley and in IT industry. The legacy and the startup companies is just growing and is in fact, the state of California keeps track. $180 billion a year is the economic impact, not the valuations of the companies, but the money spent in California in aerospace and defense. That is bigger than Hollywood. It is a huge industry only in aerospace and defense. You see there the Mandala logo where we are in Pasadena, JPL and Caltech, many, many other institutions. The number of companies and the startup companies emerging in the space business is just remarkable, really impressive. In Mandala Space Ventures, in my new job, we have strategic relationships with both academia and institutions like aerospace corporations, also in El Segundo, the US Air Force, Space Force, AFRL, and certainly with the universities, Caltech, UCLA, and USC, who are all very active in the space program. So I'll spend just a few minutes about my business, what I decided to implement. And some of you may have heard in the past, at least I've discussed before, in Pasadena, there is a venture studio that's been around for over 20 years called Idealab. Bill Gross, Larry Gross, two brothers from Caltech, started Idealab, which is a venture studio. And that model is a little bit complicated, but it simply consists of two companies. One is a studio. Think of it as a think tank where companies are created, where founders and CEOs come to you with an idea, or they can be entrepreneurs in residence to create an idea. And then you have a separate company, which is just an investment vehicle. You collect money from what are called limited partners, you create an investment vehicle, and then there's a balance between the two. The think tank creates ideas and companies, and the venture fund invests in those companies. So that's combined, called a venture studio, and that's what Mandala Space Ventures is. What I'm showing here is some of the companies on the left from the studio, and some of the companies on the right from the venture fund. The venture fund can invest in the studio companies, doesn't have to, but also invests in other companies. So the venture fund has a fiduciary responsibility to the limited partners to make return on investment. And at an arm's length decides whether to invest in a studio company or not, and can invest in outside companies. When a fund invests in the studio company, the studio never prices the companies coming out of the studio. There has to be a third party that says, I think this company is worth so much. And then the fund can invest at that price. This is a little bit detail, but you see, is there a pointer here, I think? Yeah. These are some of the companies that we invested in from our first fund. You may recognize Anduril is a pretty big defense contractor, also in AI and drones and so on. Anduril actually bought one of our companies, Adranos, and we were very, very lucky. They bought it for shares. So the fund has Anduril shares, which have grown considerably. We also, Varda is now a unicorn, over $1 billion. They do manufacturing in space. Stoke, wherever Stoke is, yeah, Stoke here from Seattle is a launch vehicle company that only recently, a few weeks ago, closed a $500 million investment at $1.9 billion valuation. So we're very proud of that investment as well. Link Global is doing satellite to cell phone broadband communications. They're doing very well. Ursa Major from Denver is another company that is doing extremely well in the propulsion technology, lunar outpost, and so on. And here I will talk a little bit more about Sophia Space, which is data centers in space. So besides our studio, and this may be relevant a little bit to Santiago, to Chile, maybe some other regions in South America, we also run an accelerator program. What that means, I'm not sure people are familiar, but an accelerator program is like your Shark Tank, if you watch on TV, where companies come to you and you invest in existing companies at an early stage. We run a program, an 8-week program, where we do a competition, we select startup companies, we then mentor them over a number of weeks, and then we introduce them to over 100 VCs in the space business. In the US, the most famous accelerator program in Silicon Valley is called the Y Combinator. That's where Sam Altman came from and so on. They're the most, they're not thematic, so they're very broad. You can do Bitcoin and you can do, wellness companies. They all fit into the Y Combinator, whether it's an Uber or Airbnb and so on. We run accelerator programs only for space, and we try and make it as thematic as possible within the space program. We've done that now so far for the Canadian Space Agency. So the Canadian government reached out to Mandala and said, would you run a program for Canada? And so we did. And a lot of these companies that went through our program are doing quite well. Aurora Tech is a satellite company, a constellation looking at fires, early detection of fires. They raised a $38 million round. Another company, Volta, is doing optical-based power delivery on the moon. and so on and so on. A few, Reaction Dynamics is a launch vehicle company. Wyvern is a hyperspectral imaging platform, and so on. So as part of our program, we bring in JPL, aerospace. It is a really successful program, and we want to do more of those internationally. So if anybody is interested in talking about whether Chile with another country or only Chile is interested in doing a space thematic accelerator, we can certainly provide that. This is another one we did for the UK Space Agency. And this is, we gave them a tour of Rocket Lab. VAST is a company, and all in Southern California. VAST is a company that's doing a private space station. And Rocket Lab is a publicly traded company doing launch vehicles. And these are the companies that went through our accelerator program from the UK Space Agency. These are some of the companies that we are incubating in our studio. So in our studio, we have people, professionals, space engineers, and across many, many domains. And we look to create new companies as often as we can. It's quite hard to create a full-scale startup company with finance and so on. But these are some of the areas that we have invested in. Spectre is a hypersonic vehicle engine. We have a startup company we're incubating in imaging hypersonic vehicles. Viridian is, as I mentioned earlier, a very low Earth orbit propulsion engine company. They just won a few contracts. And I'll talk to you a little bit more about Sophia Space right now. So Sophia Space is one of my very proud to say recent companies, together created by JPL, people from JPL, Caltech, and Mandala Space Ventures. The idea for Sophia Space, Sophia name came from the Greek word wisdom, and the tagline was wisdom above the cloud. So that's where Sophia Space name came from. The vision for this originated a few years ago, and it's a very nice story that I'm happy to share here with you. Caltech has had, for the last 10 years, a donation from a private entity, from Donald Bren Foundation, of $100 million. So Donald Bren, who's a real estate mogul in Orange County, donated to Caltech $100 million 10 years ago. That doesn't happen every year. And that $100 million donation was specifically for the Space Solar Power Project. Space Solar Power. How do you build infrastructure in space and beam power down to Earth? The approach they took was to have large data structures in space, very large, and then convert energy from solar rays, energy collected, into RF beams. So through conversion from electric energy into antennas, little mini antennas, in a very large area, beam those down into receivers, just like you have arrays of solar rays on Earth. Imagine arrays of RF antennas. They collect energy and then connect to the grid. Well, after 10 years, I hate to they're all wonderful people and friends, but the business case did not close effectively to commercialize it. The technology was developed, but the business case really was a very hard sell to compete with energy on Earth and so on. So a few of us from the Space Solar Power Project came to Mandala and from JPL, and we said, well, what if we don't beam down energy? What if we beam data? Forget about trying to close the energy gap. Let's put some computing into these structures and just do all the edge computing in space and beam down data. Laser comm, RF, whatever it takes. And that, all of a sudden, the business model closed. Especially when we saw what was happening, and this is before ChatGPT. this is around 2022, 2023, we started listening, and here are some of the headlines we took from, and I purposely for Mark put the first headline there for Microsoft. We saw from the Semiconductor Industry Association, it's not here, but I'm sure you can find it, the global energy production of the world was on a very slow slope, increasing, very slow. And then the energy for computing was on a fast-moving, exponential growth. And the two were going to cross around 2035. And we looked at that and said, oh my God, this is calamity. This is calamity. The world is not on a path to build enough energy for the computing. Then we read other headlines that Google was spending more on computing energy cost than all the salaries put together at Google. So there were alarms going off all over the place that there is an energy problem. And then I really wish I could take some credit for this, but Jeff Bezos just published a few weeks ago, he gave a lecture somewhere, I think in Milan, that he basically predicted that data centers will be in space in the next decade or two. So this is how we were looking at from an energy point of view. There is clearly a crisis. Now, these are some of the solutions that Mark mentioned that are all ongoing. Nuclear fusion, nuclear fission miniaturization, and we're not going to deny any of that all of this is our attempts to solve a humanity problem when it comes to energy. What we're starting to do is address one of those topics. There's no way to stop that there will be fusion at some point, energy, effective, and so on. There will be fission, miniaturization, and so on. But space has some advantages. And I believe technology is moving in this direction. Launch vehicle costs are coming down. Infrastructure build in space is coming. Free energy from the sun, free cooling from deep space, and I'll go into that a little bit more. So there's no doubt that all of this is taking place, nuclear fusion, and fusion and fission and hydrogen energy and so on. But this is another alternative that I believe is our destiny. Now, I do not believe that it will, in the next decade, compete directly with data centers being built and say, let's build them now in space. So I think it's going to be gradual, and that's what Sophia Space is doing right now. So what is the advantage? And there are some disadvantages, but there's limitless energy from the sun. In the orbit that we designed, there's no day and night. There's no atmospheric interference. There's no attenuation as bringing like solar rays on Earth. So you really have limitless energy depending on the area of collecting from the sun at no cost. Natural heat sink. Space is naturally, deep space is 4 degrees Kelvin. It's very hard to reproduce that kind of a cooler on Earth. There is research on millikelvin, superconductivity, and so on at a very high cost. But 4 degrees Kelvin is your natural background temperature of space. So if we can somehow constantly face the sun with solar rays and constantly radiate into deep space, that is actually referred to as a sun synchronous orbit. There are existing orbits that we can launch into that are constantly facing the sun and constantly radiating into deep space. Low latency of communications. Not many people realize that space or low Earth orbit is very close. 500 kilometers, 600 kilometers, that's nothing. So it's very low latency. There are some people who have proposed geostationary or even the moon. Those latencies are way too long. So we want these latencies to be in the low milliseconds, just like we're used to on Earth. So spaceborne edge computing, our first instinct is to not try and compete with any of the terrestrial data centers. Let Microsoft build Wisconsin, Virginia, you name it, all of those are going to happen. What we're proposing is to be a adjunct or a surge capacity or a beginning of an alternate energy capacity for doing edge computing in space. There's no way that with today's capabilities and where we are today, that a data center in space on a small scale should or can compete with data centers on Earth. However, as you'll see in the next slide, we really want to target these data centers in space to add value, not to be competitive. And the way to do that is to put these data centers in between the broadband communication layer, the Starlinks, and the Earth observation satellites. So imagine if you have a constellation, so this is one module, another module, communicating with optical communications. And today, optical communication, free space optical communication is standard. Starlink has it, Kuiper, Viasat, and so on. The standard today is about 100 gigabits per second. The already in the laboratory is 400 gigabits per second bandwidth between satellites coming into reality. So today in space, 100 gigabits per second, free space optics exists. 400 gigabits is the next step, which is within a year or two. So imagine here you have modules, each one of them launched, maybe a few of them on a Starship. These dimensions today, the capability that is in the works, you can look at a company called AST Mobile. They're doing broadband communications between satellite and cell phones. Their dimensions for their phased array antenna is 20 by 20 meters, imminent, being built right now. 20 by 20 meters is pretty large area for a small data center module. When we did a comparison with what's going on Earth, we basically said, how can we build a 100 megawatt data center today? 100 megawatt data center, we actually compared it to an Apple 100 megawatt data center being built, I think in Iowa. And we looked at the budget that Apple published, 1.4 billion, a few years ago, and we actually did a very detailed model comparing the cost of launching 100 modules, so 100 modules in low Earth orbit, each one of them to be a megawatt. So this dimension would be 50 by 50 meter, so it's not 20, but 50 by 50 meter. It would be 2,500 1 by 1 meter tiles, as you'll see in a minute, and then 100 of them launched on a number of different launch vehicles. When you look at the total cost, in today's cost, it was pretty comparable. And that's without the advances in reduction in cost of the launch vehicle, manufacturing, and so on. And all of these costs that we included here included the equipment. Now, how does this actually? Yes, yes. Does that include the operating cost? Yes. No, it included the operations cost. In fact, the operations cost was the smallest. This is where you save all the money. The big cost is in the launch vehicle cost and the CapEx. The operations costs become virtually none. You don't pay for the energy. The way we design the system, and we're building it right now, is that it uses a lot of the technologies that were developed over the decades for space. Nobody asks who is maintaining GPS satellites. They're there for the last 20 years. When we need to replenish, we send another GPS satellite. So these modules can be built to be fault tolerant in the relevant radiation environment, to be self-repairing, self-healing, and so on. And that's how they're intended to be. No maintenance. If a module fails, a server rack fails, and you'll see how that looks, then it can take itself off the grid, and so on. So this is the still division. I wanted to share with you the general, how should I say, the general trend. When we look, at least from my JPL experience, we have a joke that when you design a new mission, you only allow one miracle. If you design a mission with 2 miracles, you're in trouble. 3 miracles, you're out. So we're only allowed 1 miracle. So when I looked at all these areas of endeavor that are happening right now, heavy launch vehicle, I went already through that. Thin film solar rays, there is a huge industry to reduce the cost of solar rays in the world. And a lot of them are also radiation, some of them are radiation tolerant, perovskite solar rays, and so on. If you look at the solar rays today on the space station, they're extremely expensive, about $400 per watt. The target value of solar rays for space is $0.02, so 2 cents per watt. So there's a movement at foot right now to reduce the cost of solar rays by 4 orders of magnitude. This is enabling, hugely enabling for data centers in space. Flexible electronics. In the US, there's a huge consortium, US government, academia, on what is called Next Flex. How do you embed electronics into flexible structures, thin film, membranes, and so on, as shown on this picture here. This is irrespective of anything that we're doing. Satellite companies, we're currently partnered with a company called Apex, that this year, it's in the public domain, this year they've raised twice $200 million to build low-cost, massively manufactured satellites. So the whole area of low-cost satellite buses is coming down. This is an area that NASA invested huge amounts of money, and Caltech, called large deployable structures. This is basically an origami approach where things are stowed in a very small volume, you launch it into space, and then it opens up the size of a football field or more. So this is evolving. Stanford is a leader in this area as well. NASA has recently demonstrated the helicopter on Mars, the 1.1 kilogram helicopter on Mars. It actually used a commercial Qualcomm Snapdragon computer. So NASA, if you were to take the traditional space computers, they wouldn't fit. The whole computer would be heavier than the helicopter. So NASA partnered with Qualcomm and looked at the detailed radiation testing of the Snapdragon processor, requalified it for the Mars mission, and this is operated many days on Mars using the Qualcomm commercial processor. We're applying that same approach with looking at the NVIDIA processors right now. We're currently baselining using the AGX Jetson Orin NVIDIA computer. And in the architecture that we're building, we're trying to pair up the NVIDIA computers, the GPUs, commercial off the shelf. We're not changing the NVIDIA chips, but we're augmenting it with radiation-hard microcontrollers. And those are basically managing the racks of computers. Those are extra reliable, much lower cost, and they provide the backbone, the radiation-hardened backbone of the data center. Other areas, optical comm is right here, mesh networks are right here for broadband communication. So what the one miracle that we basically are focused on is thermal management. This thing is going to get very hot facing the sun and very cold facing deep space. So if you look at this is an example, this is certainly a rendering of a single tile. This is a canonical 1 by 1 meter tile. The solar flux in roughly 600 kilometers sun synchronous orbit is about 1.3 kilowatts per square meter. And that's just the natural radiance from the sun. There are techniques, available techniques and flown techniques to put little solar concentrators on the solar rays and get more energy into the same area than 1.3. So you can double the energy into the solar ray with solar concentrators, and you can go even more by beaming laser energy into solar rays. So you are to the first order limited by the solar flux, but you can go a step further and step further. When you open up on the back side of these solar rays are this is what we would call a rack. Our rack is 4 computers, 4 NVIDIA computers with a rad-hard microcontrollers. And this is completely passively cooled by the radiating surface on the back side. I purposely did not put a diagram in here, but Mark is absolutely right. The way this would work is you get solar energy from the sun. This can get as hot as 120, 150 degrees centigrade. Then there's an insulator behind this solar ray to stop the energy from soaking into the tile. Then you have the 4 computer racks, 4 computer modules with NVIDIA microcontrollers, all the memory and so on. Behind it is a thermal spreader, like a diamond spreader, but there are many others that are less expensive, graphite material and so on. We don't need to immediately jump to synthetic diamond. And then behind that spreader, thermal spreader, is a radiator. So we have a radiator in the back, thermal spreader, the NVIDIA chips, the backplane, and then insulator and solar rays. We've modeled this, finite element models, physics-based models, and so on. And our challenge is to keep this warm enough. So this is the reverse that we have on Earth. This is biased cold. So even if somebody says, okay, there's nothing for these things to do, yes, we need those heaters, those GPUs as heaters to keep it warm. And also on this module are batteries that store energy so that even if you need extra computing power, you can use the battery stored on the tile for peak performance. So what is the one, I would say, limitation of building a data center? Oh, and I didn't say, if you tile these, if I go to the next one, this is our first design of a spacecraft module with a number of tiles here on both sides. We call this one a tile. And these would be deployed using standard solar array deployment technology. So we're not inventing anything new here other than the thermal design. So this is stowed when it's launched, opened up when it's deployed. This in the middle is a standard Apex, K2, whatever satellite bus. It has communications, it has its own avionics, it has regular spacecraft technology. This is deployed and provides the data center is really the payload for this spacecraft. What I didn't show earlier at all is that the only connectivity between these tiles is fiber optic. There's no energy sharing, no power sharing, no cables. Only fiber optic links between one module and another. And those are very light, they're bendable, and they're very fast. So only connection here, there's no cables, there's no copper, there's only fiber optic links between these tiles. And they operate in a distributed fashion. So if one tile fails, or one quad fails in here, it takes itself off the grid as a distributed computing element, and the rest of the system can operate. So right now, as of today, we're building one tile in our lab. Right now, we have a functional prototype, you're welcome to visit, of a single tile in a laboratory for NVIDIA's with the microcontrollers. And we are running a lot of algorithms, a lot of stuff that is kind of standard NASA technology of fault tolerance, recovery, and all the stuff that we know how to do very well. So you can see here is another module. We call these modules, so they will be connected through optical free space optics. And I'm very excited, just a couple of months ago, SpaceX Starlink announced that they're opening up their Starlink satellites for optical communication with other satellite systems. So when we're planning to do a tech demo of a smaller version of this system, we would love to be able to, through optical fiber, through free space optics, connect to Starlink, and then be able to connect to anywhere in the world. So this is almost the end of my presentation. I didn't really go into the details, but this is already fully deployed. Our first fund that started in 2021. Now we're deploying our second fund and then planning the third fund. And these are some of the examples that I mentioned that we've already invested in: Stoke, Lunar Outpost, and many others, about 10 companies. There's a little bit more on the performance of those companies, and this is a nod to my team, a lot of them from JPL, and all the interfaces we have that we're very proud of. And I hope you enjoyed the presentation, and thank you for your attention.
Thank you, Mr. Alkalai.